I'll take one simple example, and after that I'll show why that approach we did in this is not enough. So we need to use something extra. That extra we call dynamic programming. Okay. So let me take a simple example. I'll write it. Okay. So suppose there is a hen at start of day one. Okay. Suppose we have a hen at the start of day one. So yeah, and there is one property that hen lies an egg after every 24 hours, and after every 24 hours an egg becomes a hen. And assume that no hen dies in the process. Okay, so this is the question. So what we want to know about that is what is the number of hens after day n. So just remember this question. Yeah, so what we not want to know is the what are the number of hens after day n. So let me denote of n, number of hens at end of day n. Okay, so we'll do this question by, like, first we will try with the base case and all. So what we know that at the start of day one we have one hen. So what will be the f of n? That would be at the end of day one also there will be one hen. So let me draw something like, yeah, suppose this is one. Yeah. So what happened at the end of day one? We have one hen. So when we start with the day two, there are 24 hours that already passed away, and we have, so what we have the properties at the end of 24 hours we will have one egg. So this egg will come up in the start of day one, but at the end of day one this egg still be the egg because it takes 24 hours. Like, assume that this is little more than 24 hours, so it will take 24 point something. So there will still be one hen only after day two. Is that, yeah. Okay. So what happened at the starting of day three? This hen, this egg will become hen, and this hen will produce one another egg because there are already 24 hours passed away, and this become an hen, right? So the next day, what will happen on the next day? So this egg become another hen. I'll denote like this, and this hen will produce an egg. So 24 hours are passed, and this have another egg, this have one egg also, because more than 24 hours again it will produce an egg, and this hen just will like born. So what happened on the day at the end of day 5? This egg will become hen, this egg will become hen, this will produce one egg. Okay, so there are now how many hens? So there is one egg, there is one egg, there is one egg, and there are two hens more. I'll draw here. Yeah. So what we can see from here is that at the end of, like, suppose I'll take one another, so there will be three more hens and five more eggs. So basically three more hens. So these are the fives I'm drawing that we have already. These all will have their egg and three more hens, right? So what we can see from here is that, like, if you can see, what are the number of hens at the end of day n? So basically, suppose we'll take day 5, right? I'll take day 5. So on day 5, we have 1, 2, 3, 4, 5 hens and 3 eggs. On day 4, we have 3 hens and 2 eggs. On day 6, we have 1, 2, 3, 4, 5, 6, 7, 8 hens and 5 eggs. So these 5 eggs are coming from these 5 hens, and these 3 extra are coming from these. So I write this as f of n is f of 6. Suppose f of 6 is number of hens, that is f of 5, plus number of hens that got from egg new, that is f of n minus 2. You can see that this is the case. So suppose I take f of 6, then this, what will this, f of n minus 1 is 5 here. These are the 5 hens, and the 3 new hens are from egg. How many eggs are there? How many hens are there on the day n minus 2th? So this is the recursive relation we got. So now we got the sequence. So what we want to do is compute the value of f of n. So suppose I want to compute for f of 4. Let me take f of 4, and here you can see that base case are satisfied, which is f of 1 equal to 1, f of 2 equal to 1. We will take these as base case, and now f of 3 will be, what is f of 3? F of 3 will be f of 2 plus f of 1, that is 1 plus 1, that is 2. F of 4 would be 1 plus 2, that is 3, right? And here we can check also, this is 3. So, like we are doing that. Okay, so how we are computing this is, we know that how we compute for Fibonacci sequence. So we'll take one f of n, we'll compute for f of n minus 1, f of n minus 2, and for n minus 2 here also n minus 3, and so on till we find out the base case. So can you tell me what are the computation we are doing? So basically, how many computation we are doing? We are doing, actually, if you can see that we'll do something, not like for every step we are making some 2 computation, and this should not be 2, it should be low, something less than 2 power n computation. So I know what is the, like, correct time complexity of this. It is actually O of 1.618 raised to power n. Okay, so this is the time complexity. So suppose I want to calculate how many hens are there at the end of day 30, n is equal to 30. So what should it be? Or 1.618 at the power of 30. It would be a very big number, right? So it would be around something 185. I have already written that, 9325.9, something like that. So this is the number of, so we can calculate for 30 days. But suppose I ask you, what is the time complexity if we want to calculate for 1 year? So that should be 1.618 raised to power 365. This number I can tell you, this is 1.893 into 10 to the power 76, this much. So here we can see that even the best computers, supercomputers, they can't handle this value. So how we can like solve this, right? So here we can see that, so now there comes the optimization. So where here we can see that for every smallest subcase, so suppose there is f of n minus 2, we already calculate f of n minus 2, but where here we are also again calculating f of n minus 2. So basically we are making computation again and again. So to make it simpler, can we just something do like learn from our previous calculations? So what we do is we'll store this value somewhere, and when we need this we just call this value. So it shouldn't be taking of n 1.16, something like that, 6 power n minus 2. It should be done in O of 1 because we already know that value. So yeah, so how we can do is, so suppose we are calculating for f of, this is n, this is f of n, 1 1 2 1. So for 3 we know we want f of 1 plus f of 2, that is 2. For 4 we know 2 plus 1 3. So when we are calculating for, so I'll take one another, 5 6 8. So when we are calculating for f of 6, what we are doing is calculating for f of 5 and f of 4. Now when we are calculating for f of 5, we are doing for f of 4, f of 3. So what easily we can do is we compute for f of 4 here already, because we'll use this data like for while calculating for f of 4 we'll need f of 3 plus f of 2. So we are already doing that previous calculation, but we are now, if I want to evaluate for f of 6, I'm again doing for f of 5 then f of 4, but we already done that for f of 5. So basically f of 6 ke liye we already done that f of 4, and for f of 5 I'm again doing f of 4. So how we can optimize this is the question. So what I can do is make some array of f of n. I'll store the data while when I calculate f of I. I'll store this in, like I'll take this as a index. Yeah, so when I am calculating f of I, I'll store this in a of I, and when I need to check this again, I'll just call this. If a of I is already present, then we will not do this computation again. If that is not present, then we will do this computation again. So let me just explain what with a simple coding. So let's code this. So what I want is to calculate the Fibonacci number at the nth index. What is the value? So I take n and I'll see in n, and I'll just make one function. What this function does is it will return the value function, and the input would be the value of n, right? And what is the base case? First I need to calculate the base case. So this is the naive approach of solving the Fibonacci number. So I am doing this by recursively. So my base case is if n is for me it was for n equal to 1 and n equal to 2 it should return 1, right? So I'll write this as if n is less than 2 return 1, else I need to return function of n minus 1 plus function of n minus 2, right? And I just call this function here, cout function of n, right? So this should run. Yeah, so suppose I type 1, it is expected. 2 expected. For 3 it should return me 2. Yeah, for let me just take 6. For 6 just we saw that it should return me 8. So yeah, so this is working fine. But here is one problem. So for example, for the day 30, I'm writing day 30. It is working because it is like 6 digits. We can do 10 to the power 8 computation in 1 second. Suppose I write day 42. Yeah, so here you can see that it took this much time, right? So, so if I write something bigger than suppose 44, so it is taking much time. So if I increase, as I increase my n, so if I put some 365 here, it will not finish, like not now, like even if I check after 1 hour or 2 hours it will not finish. So how we can optimize this, right? So time complexity here is some, oh, as I told, of 1.6 power n. So how we can optimize this? So what we can do is, instead of doing that, right, so I'll make one array to store what are the values we got in previous indexes. So this array will be a of n, suppose n plus 1. So here a of 1 denotes, I'll just comment this here. Here a of 1 denotes Fibonacci value of 1, right? And so on, right? So I'll just initialize this. First I'll initialize the array I is less than equal to n. So basically it is less than equal to n plus 1 plus I initialize this with 0. So some people do with minus 1, but it's a choice, right? So I'll initialize with 0, right? Now what is the base case? A of 1 is equal to 1, a of 2 is 1. Now for every 3 I is less than equal to n plus I, what I want is I'll take the value from ith index. So basically f of I, if I write f of I here, so this would be f of 3 for I is equal to 3. This would be f of 2 plus f of 1. So f of I minus 1 plus f of I minus 2. Not f, it is a, right? Okay. Right, so a of 3 we stored here. So if I goes to 4, we have a of 3 already just calculated and a of 4, right? So from this we are storing the values in the array, and we are not computing it again when we want it. Like if this value is already present, that we know, because I minus 1 is calculated before I, because we are using the loop in linear machine, and I want to print the value of a of n, right? Okay. I'll run this now. So I'll check for the base case. Yeah, it's working, right? For 3 it should give me 2, right? For 6 it should give me 8, and for like 30 it is, see, this is very fast. So if I write 42 here, it's fast. If I write, suppose, 50, so this negative value came because I have used int, so I should have like used hash define. It should be int 32t. Yeah, so if I write 5 6 here, it's getting it. If I write 50 here, I'm getting the value, and it worked like very fast. So this is basically O of n, because I just did the one linear search, and I'm using the space. So time complexity will be O of n, but I have used that extra space to make that array. That is the space complexity we say. Okay. So yeah, now you can see that power of dynamic programming. So I just solve a long problem which takes my days to solve this, but I can solve this. So I'll try it with, suppose I'll try with 100. So yeah, so here you can see that this came up very fast. But if I do with the O of O of 1.6 power n approach, then it should be very long. And this is the power of dynamic programming. We are able to solve a pretty huge problem in a small amount of time by utilizing some extra space. So yeah, that's why we need dynamic programming.